What time are we supposed to start? Or
more or less, it depends on the chairman and of the speaker. So both are here. Chairman is Mitrosha Poval, you are the speaker, so we can.
Whenever.
You are ready. Good.
Shall I start sharing my screen?
Yes.
Okay. Probably I should start and briefly introduce, first of all, myself. My name is Dmitry Poval, and I'm junior researcher of the Laboratory for Statistical Physics of Complex System at Institute for Condensed Matter Physics. And I'm pleasure to introduce our first speaker, Marc Barthelemy. Is now research director at the Institute for Theoretical Physics in Saclay, and a member of Center of Social Analysis and Mathematics at the School of Advanced Studies in Social Sciences. And Marc's field of scientific interest is very broad, from disordered system and their properties in past investigation. In particular, his thesis in theoretical physics and at the University of Paris 6, titled Random Walks in Random Media. And now he worked at statistical physics of complex system. In particular, he worked on complex network, theoretical epidemiology, and on problem in urban system. And today, Marc talk about stochastic equation and city growth. So, Marc, please.
Thank you very much, Mitro, for this nice introduction, and thank you for inviting me. So let me select this. This should work. Do you see something?
Not yet, I think. No. Yes, we see. We see your
yeah.
screen. Yeah.
You see the screen?
Yes.
Yes.
We see the presentation.
Okay, great. Okay, so if it works, I can start. So thank you for having me here. I'm of course happy to make this speech in this conference, and I hope next time it will be in person, of course. And so I will talk about cities and basically a quantitative approach for cities and for the population. And I won't say many things about cities, just few facts that you probably know. On the top, you can see the number of cities with more than 1 million, with population larger than 1 million. And basically this number is going towards 1,000. This is in the world. And the mega cities, it's the bottom plot, with population larger than 10 million, this is of order 40, 50 in the world. So these large cities will be more and more important, especially in emerging countries. And the fact that you have to remember is that this is very localized. It's less, all these cities together, it's less than 3% of the emerged land on the planet. But it represents 70% more or less of CO2 emissions and 80% of the wealth, of the total GDP. So it's really about concentration, and it's really where humans, in fact, live on this planet. So it's really important to understand these systems. So this is basically, there are many other reasons, but this is the main reason. We need to understand this. And what statistical physics can do for it. And in fact, there is a long story. I won't spend too much time on that, but it started with a long time ago in the 70s. There was already this Schelling model that in fact is close to a spin model. And it was talking about segregation, or different groups can segregate in a city. But then later, in the 80s, typically, there were many studies about fractals and cities. That was, for example, Gene Stanley and Shomo Avin in the US and Israel did a lot of studies on this. And even later in the 90s and 2000, percolation became very important for cities. And in fact, it's even now, I think, the best way to define a city as the giant component of the percolation process of the built area. And this is a long story, of course, but we saw even more recent studies about mobility and so-called radiation models, etc. So in fact, there is a long story, many interactions between statistical physics and cities. And so, and it's not a surprise that I will that in fact the equation that governs the evolution of urban population is also something that we are very used to in stat phys, which are stochastic equations. And this is what I will talk about today. Let me now just mention that the city is probably one of the most complex systems in the world, maybe with the brain and other systems. You have many constituents interacting over different scales, spatial and temporal scales. And so you have individuals, government, institutions, private companies, etc. All these agents are interacting with each other. And this, in fact, leads to emergent properties. We can see some spatial organization, mobility patterns, for example, things like that. So it's typical from a complex system. Many interactions, many constituents, and emergence of collective properties. So then the problem is really, how can we model this? Can we make some prediction? Can we identify critical parameters? And as we'll see, we are far from being able to answer all this. We just have a partial view so far. And so basically today, I will focus on one very specific point, which is the population distribution of a city in a country. So for example, you have a country, there are many cities, you can compute the histogram or the probability distribution of this population. And so what can you say about this distribution? Is it broad? Is it kind of Gaussian? What's the equation for this distribution? And also, the distribution is not enough. We also have to say something about the dynamics. What's if you rank cities, for example, are the ranks changing a lot? For example, are some cities disappearing and some other appearing and becoming super important? So, and all this, in fact, points to the need of writing the time evolution of the population. So I call it in this speech SI of t. So this is the population at time t of city I. So can we find an equation for this that explains both the distribution that I will talk about in a minute and the observed dynamics? So that's the main problem I will address today. Yes, maybe let me skip this. I hope everything is okay. Let me know if you have problems. So let me start with the first important empirical observation about cities. And it dates from more than 100 years ago. And the physicist Auerbach, German physicist, did something. I don't know exactly why he did this, but he ranked the cities according to the population in decreasing order, and these were the cities in Germany at that time. And you see on this, for example, at that time Berlin was the largest city, and here it's in thousand. The population is in thousand. So Berlin with approximately 3.5 million inhabitants, then Hamburg, etc. And he noticed something is that the rank, so Berlin, it's the largest city has rank 1, the second largest has rank 2, etc. He noticed that if you multiply the population times the rank, it's approximately constant. So let me show this this is his plot. So you see, this is what he called the product. He called it absolute concentration. And so versus the rank, so he really looked at this product, and here it was about 50 here. So it's more or less constant. And this was really the first observation about the distribution. And in fact, a bit later, 20 years later, 30 years later, Zipf redid this analysis, and here's the plot for the largest metropolitan district in the US, and here it's population versus rank, and he found indeed something which is approximately inversely proportional, meaning that the population S at rank R is approximately 1 over R. You can generalize to some exponent nu, and the exponent nu is very close to 1. So he generalized this result of Auerbach to many things, to words and books, etc. And now people are talking about the Zipf law, in fact, which is this kind of relation between the variable of interest, the population here, and the rank. And this is, of course, very important because it tells you if indeed it's 1 over R, it means, for example, that the second largest city has basically a population half the largest city, etc. So it's and in fact, it also means that if you know the population of the largest city, you can deduce the population of all other cities, knowing their rank. So it's a highly non-trivial thing, and people discuss that for until now, so more than 1 century. And it was, here's another example, a more recent example. So you see, of course, some deviation. You see that it's not completely a pure, nice power law. There can be some problem, but I will come back to that, of course. And yes, just to mention, just a quick digression. Of course, to us physicists, it's maybe not a surprise that we have such a large range of cities, such a hierarchy from very small, medium, and super large cities. But for an economist, for example, that's a very surprising thing, because if you think that the city is an outcome of some cost-benefit argument, let's say, there should be some optimal population. And so, in fact, this puzzled a lot the economists. Why do the population of cities not converge to the same value, in fact? And how come that we have such a variety, such a diversity of population? And we will try to give a reason in this talk. So there's another consequence of Zipf, of this Zipf law. And here's this quick argument, is that if the population is like 1 over the rank to some power alpha is usually close to 1, then it also means that the rank is given by basically the cumulative from S to the maximum value of cities. So for example, if S is very close to S max, this integral is basically of order 1 over n. Rho of S is the distribution of cities, and 1 over n times n makes 1. So that's the basic argument. So anyway, from this, you can show that if you have a Zipf law with exponent alpha, then the distribution of cities, of the population, is 1 over S to some exponent, which is 1 plus 1 over alpha. And which means that the smaller alpha, the largest this exponent, and the more homogeneous the city distribution. And for alpha close to 1, which is basically coming from empirical studies, this gives you a distribution of city sizes going roughly like 1 over S squared. So this is really a broad law. There is the variance is basically infinite. So the fluctuations are super large. We are very far from some, let's say, optimal value where cities have more or less the same size. This is definitely not the case. We have super large fluctuations, and typically the size of the largest city in the country is of all the total population of all cities. So that's the let's say a feature, an important feature of broad laws. So it's and the fact. So then people started to ask themselves, okay, what would be the simplest model? And here the simplest stochastic differential equation that could describe this Zipf law. And the main idea, the main model is coming from the Gibrat model. And Gibrat proposed this equation here that the quantity at time t plus 1 Here it's the population. At that time, Gibra did it with the size of companies, but it was quickly transposed to the city case. So here the size, the population at time t plus 1 of city I is basically the city size at time t times a factor, which is the growth rate, typically. And this growth rate is supposed to be independent from population, and typically something like, for example, Gaussian or random according to a certain value. Here it must be something like larger than 1, typically. And if you write this model, so eta here typically would represent something like the demographic growth. So it's really the balance, the budget between birth and death, typically. So this is the simplest equation that you would write with this multiplicative noise. But if you write this, very roughly speaking, you can convince yourself that S at the population at a certain time will be the product of this growth rate. And if they are independent variable, typically if you take the logarithm, it will give you the sum of the log of eta, so a sum of random variables. So the log of population will converge to Gaussian, according to the central limit theorem, which means that the distribution of a population will be log normal. And this is not consistent with empirical data. So if you take the simplest model, this Gibra model, it doesn't work. You cannot understand the Zipf flow. And so what happened is that in 1999, an economist, Gabet, a French economist who is now a professor at Harvard in economics, proposed to modify a little bit this Gibra model by adding the condition that there is some minimal threshold, meaning that the cities cannot disappear. I mean, their size cannot be below a certain value. And there are two ways to see this process. So the first way is that you write that the population at time t plus 1 is again this eta time s, so you have this growth rate, plus some random noise that is strictly positive. And this is how it was studied by Kesten, who is a famous probabilist, a mathematician. And there's another way, maybe closer to a physicist mind, which is taking the log of this Gibra model. So you take x, it will be the logarithm of the population. L is the logarithm of this random variable, which is positive. And you have a barrier, which is the log of the minimum population that you allow in the system. Again, here in the simple model, you don't allow the population to be below a certain value, which is here S min. And then you can rewrite, it's very simple, this model by with this following equation, which is x at t plus 1, at time t plus 1, is x at time t plus L, which is this logarithm of eta, except if it's below the minimum value. If it is, you set it to equal to this minimum value. So it's really a random walk, but with a reflecting barrier at x naught. This is another way to see it. In addition, Gabet imposed another condition, which is that the average of the logarithm of eta, this random variable, is negative. So basically, you have a random walk, but with a kind of flow which goes to the barrier. And what you can show is that, maybe I will skip all these details, but you can show that this random walk with this barrier, you have to write, if you want to solve that, you have to write some kind of equation, integral equation for the probability to be at position x, which is here, which is basically the probability to be at x minus L times the probability to jump L, and this gives you the probability to be at x. And this type of Wiener-Hopf equation can be solved. There are many tricky points, but when you do all the math, you get that the probability distribution of city size is indeed the power law of the form 1 over S 1 plus mu, where mu, this exponent, is typically 1 plus something going to 0 with the threshold. And so what does that mean? Is that Gabet, in fact, in his paper is cited 2,000-3,000 times. People were very happy with that, because here you have some relatively simple process, and it gives you a probability distribution with exponent 2 as observed in the data. So this is consistent with the Zipf flow. And this was in 1999. So at that time, everybody was happy. There was this Zipf flow. The model is the Gabet one. So everything seems to be solved. Of course, there are many other competitors, but different models, more or less realistic. But the most accepted one was the Gabet model. And the fact is that after 2000, we had always more data about city population in different countries, but also historical data. And so people started to check the Zipf flow for many, many countries. And here is the result of some meta-analysis done by a French geographer, Cotineau. And here is it's the histogram here of the Zipf exponent, this alpha value. So Zipf, strictly speaking, found this value 1. But if you look on almost 2,000 estimates for different countries, epochs, etc., you observe a large variety, in fact, of values, going from very small values to even values equal to 2, 3, etc. But you absolutely have a large diversity of value. And so, and this is not even counting the cases where the fit is terrible. So you don't have a nice power law. So you cannot even make a fit. So the conclusion is that there's something fishy here. The Gabet model predicts some always a power law, and with an exponent 1. And it seems that we are really far from this. So then, seeing this, we tried some other strategy to understand this. The point is that very differently from previous studies, we won't try to explain Zipf. It's true that most of the papers, they were really focusing on the Zipf flow, and they were thinking about, all these authors were thinking, how can I construct a model that will give me a Zipf flow? And so I guess that most of you are statistical physicists, and you can imagine many stochastic processes and many processes that will indeed give a power law distribution at the end. And most of the people were thinking like this. But here, we won't try to explain Zipf. We won't assume that it's valid. We will just think about what would be the equation, the evolutionary equation for the population, starting from, let's say, basic principle. And we'll see what it gives. And so let me describe this. This is the most very important slide. So why a city is actually growing? And in fact, there are not so many reasons. The first reason is that if you consider a city I here in green, there is a natural growth, which basically is the balance. It's the demographic growth. It's the balance between birth and death. That's the natural growth, let's say. There's also an international flow. Some people from other countries. So yes, I should have said that, of course, you have to define a system. Here, typically, it's a country. So you consider only cities in this system. So what is coming from out of this system, typically international flow, people coming from other country and go directly to city I, that's another source of population growth. And then there is another last reason, which is the interurban flow. Just people moving from a city to another one. And so if you want to write the variation of population of city I, it's then the sum of these three terms. That's it. There's no other reason for a city to grow or to shrink. What we did is that we put together the international flow and the natural growth. In fact, international flow in most of the data that we had is really negligible. So in fact, you could even forget it's really less than a few percent, so it's very small. So anyway, we took it together with the natural growth, and we wrote it under the form of a growth rate times the population. And this is the first term. And then the interurban flow, you can write it as a difference of flows, the incoming, Jij, minus the outgoing, Ji, between the city I and city J. And if you look at the city I, you have to sum over all other cities J. So that's very simple. That's interurban migration. And the point is, we have these two terms. What does the data say? What we can measure these terms empirically, or are these terms? And for this, we used these open sources, relatively recent, not over a super large time range of 5 years, typically, or 6 years, and for the US, France, the UK, and Canada. And in fact, the bottleneck here is to find the data, which is difficult to find, is actually the interurban migration. This is difficult to find. In most cases, you don't report going from a city to another one. It's not that easy to get. Anyway, so we use these different data sets, and what we found for this for the first term, the growth rate eta, and this is the distribution of eta, we found it to be very standard. Actually, it's typically a Gaussian type of noise with a certain average and a certain variance. So it's really these two first terms, we can really write them with this multiplicative noise, which is Gaussian. So then, of course, the more interesting term is the interurban migration. So the first thing that we noticed is with how many cities do you exchange people? So what's the number of neighbors of the city I, which typically are city J, for which the flow is larger than, which is positive, sorry. And we found that typically the number of such neighbors, so the number of cities with non-zero exchanges, is growing like the population to some exponent, which is typically of order 1/2. This is the example here shown for France. And it means that basically the larger the population, the larger the number of other cities you are exchanging individuals. So that's not a difficult thing. Now, here's the basic problem is that we have to go further about the flow. What can we say about this flow from a city I to a city J? And we started with the usual assumption, and it's well known in spatial economics and transportation. It's called the gravity law. So, and they called it for a long time like this because it says that the number of people going from I to J is proportional to the product of population, basically maybe to some power mu and nu, divided by distance to a certain exponent sigma. So this is why it's called the gravity law with reference to Newton's law. And so we use this very standard form and the different data set, and there are two main conclusions. The first important conclusion is that the exponent mu and nu are basically equal. And here are the different values for the US and France. So it's basically symmetric in the population. Then the other important conclusion is that the distance, it's the denominator here, has no impact, in fact. It doesn't explain much of the variance. Including the distance or not doesn't change, in fact, many things. The variance, it doesn't explain much of the variance. So we made a simplifying assumption. We forgot about the distance, and we write this flow as the product of population times a random variable, which will encode everything, the noise, the distance, and all the things that we cannot really describe precisely. So, and this random variable will, so with the correct normalization, we'll have an average 1. I recall that the exponent mu and nu are equal. And the fact that these exponents, I should have said, the exponents are equal, means that the average flow from a CTi to CTj is equal to the average flow from j to I. So it's a symmetric flow on average. So then you can write, you can introduce this variable x here, and you can see that the sum of all flows, you can rewrite it as that, and we can introduce all this term as capital X, which is the difference of this small x times the population to some exponent. And why are we doing this? Because then we see that here we have a sum of random variable, and this random variable, capital X, we have to specify them. And then in your term, in your equation, you will have the sum of these random variable. So we really have to know these capital X. And the empirical analysis shows us something that actually was unexpected, is that this X, which is really the difference typically of flows, which is 0 on average, so the capital X is as a 0 average, but is, here I show the positive part, is broadly distributed. So here typically there is a power law fit. The exponent is of order 1.4 here for France, probably 1.3 for the US. So it means that for positive, and we have the same analysis for negative value, we have a broad law. So we can have super large fluctuation. So the flow, even, I mean, the difference of flows between two cities is 0 on average, but can have super large fluctuation. And the exponent here is, this alpha is here is between 1 and 2. So it means that this distribution is with exponent between 2 and 3, typically. Here are some values. We tested different methods for computing this exponent. And typically it's 1.2, 1.3, sometimes 1.7, depending on the method, etc. But anyway, it's a broad law. And so let me make a recap then. Where are we from the empirical data? We have the first term, it's a Gaussian growth rate. That's fine. Then the inter-urban migration term here, we can rewrite it as a sum of random variable, capital X here, and this capital X has an average equal to 0 and is a broad law. So this is where we stand. And this is really coming from the data. We did nothing fancy here. And so the point now is that we have this sum of capital X, so it's a sum of random variables, and these random variables are distributed according to a power law. So we have to be careful. You cannot apply the standard central limit theorem, because the central limit theorem, which tells you that the sum of random variables converge in law to a Gaussian distribution here, is not correct. Because the variance typically doesn't exist. So you cannot apply bluntly the central limit theorem, but you have to use what is called the generalized central limit theorem that you probably know, and that in fact gives a result for the case where you are summing random variables when the second moment doesn't exist, or even the first moment doesn't exist. And the result is basically this one. It tells you that if you have to normalize properly this sum, and if you construct this variable zeta here by normalizing over n to some power 1 over alpha, where alpha is the exponent of the power law distribution for x, then this quantity has a nice behavior and follows, so not a Gaussian, but the generalization, which is called the Levy stable law with parameter alpha and some other parameter which are not super important. So it means that then this zeta is relatively well defined, and in fact the details of interurban migration are not so relevant. You just need to know their distribution, and in fact, since you are summing the individuals coming from many cities, the detail of the flow, the microscopic flows, are not important. So this is just to show you, this is a fit, for example, with the Lévy stable law for the positive value or negative values. This is for France, I guess. And so we are far from a normal distribution. So we really have a fat tail. And this is coming from the fact that these capital X are broadly distributed. So you will naturally get a fat tail, meaning that you can have super large values, even if the average is 0, and extremely large fluctuations. So then, where do we stand now? So we then showed that on let's say with some simple assumptions and using empirical data, that the variation of the population of a city I is given by two terms. The first term is typically a growth rate, a random growth rate with Gaussian, let's say Gaussian random noise, which is multiplicative noise. So it's an expected term, plus another term, which is less trivial, which is basically the population to some power beta. Here, the beta empirically is between 0.5 and 1, times a noise, which is not a Gaussian noise, but which is this Lévy noise with super large fluctuation. And that's the big surprise, in fact. That's this term with super large fluctuation, and the average is 0. So if maybe it could explain why people started with the Gibrat model, because in fact, if you remember a few slides ago, the Gibrat model is just the first term, basically. So the second term is on average 0. So if you forget it, you recover the Gibrat equation. So maybe it's not by chance people were writing the Gibrat equation, which is from time to time correct. But the fact that the important point is that even if this second term has an average 0, this term has huge fluctuations. And this, of course, changes a lot the dynamics, as we'll see. So in fact, forgetting about the second term is a very wrong approximation. So then another, maybe a more technical point, but it's important. When you have multiplicative noise, you have to specify correlation between the noise and the variable of interest. And here we use the so-called Ito convention and not the other one, the Stratonovich. And here the Ito convention means that you have first the population at times t, and then the migration zeta, that's the interurban migration term, acts at t plus dt. And similarly for the Gaussian noise. So we use the Ito convention. So then it's just now a mathematical problem. What's the solution of this? But this is supposed to contain everything about urban population. Let me first discuss the population distribution. There is a first approximation that you can do is to forget about the Gaussian noise and assume that this eta is just equal to the average growth rate. And then the equation that you will try to solve is this one with only one noise, which is the Lévy noise. And here you just have a constant growth rate R. And you see here, this is just a little numerical experiment. These are the two solutions with a reasonable variance. And you see that indeed taking eta equal R or eta Gaussian with a variance not too large, here we actually use the variance from data. It gives basically the same result. So if you can solve this equation, it gives you a good idea about the solution. I will, so this is maybe a little technical part, so I will go maybe quickly, but I'm happy to answer questions if you have any. How can we solve this type of equation? So it's actually like for any Langevin type equation, you have to write the Fokker-Planck equation, which is the equation for the probability to have a population S at time t. And you can construct this Fokker-Planck equation. So this is a very standard method. And the difference here, when you have a Lévy noise, which is not a Gaussian noise, is that you have to use fractional derivative. And the fractional derivative is basically, so what does that mean, d alpha over ds alpha? You have to understand it in Fourier space, and in Fourier space it will give a product k, absolute value of k to the power alpha. So that's a technical point. But you write this, you write the Fokker-Planck equation, you take it in Fourier space, and if you're lucky, you can solve it. And here, in this simple case, when you have beta equals 0 and r equals 0, for example, you get this expression, and this is typically the Levy law. So for alpha larger than 2, you recover the Gaussian, of course. But for alpha less than 1, it's not trivial, and we don't know an explicit expression when you're coming back to the X space, let's say when you take the inverse Fourier transform. So, and just to tell you how you can solve, I won't go to all the details, but the fact is that, and there's a series of interesting papers by a Polish scientist, Tomasz Stochastic. He wrote many papers about this Langevin equation with Levy noise. And you have to notice that in the simplest case, the Levy stable law can be written as a Fox function, which is this horrible thing with many parameters. It's really, the Fox function is the generalization of the hypergeometric of the G function. So it's really the most general function you can write, basically. And the fact is that it has very nice properties on the Fourier transform, multiplication, etc. So, and the idea then used by Stochastic in this paper is to try an ansatz in the more difficult case, an ansatz of this form using this Fox function H2211 and trying to solve for the small k limit. So it's the large S limit in inverse Fourier space. You can you can solve all the coefficients by solving this Fokker-Planck equation. So it's relatively involved work. It's not a trivial thing. And so you can determine what you have to take for A to t. It's actually here this coefficient, and it's basically the average population, etc. So it's I refer to the Stochastic papers if you want to have more details about that. And what you find in the end is that an approximate result valid for large S has an expansion under this form. So solving this equation is not easy, and you have this approximate form, which is 1 over S times the sum of powers of 1 over S with some super complicated coefficient. So what does it tell, this solution? The first thing is that if you look the first term here, m equal 1, so the most important term is going like 1 over S1 plus alpha. So, and this indeed corresponds to a Zipf law with exponent 1 over alpha. So it seems that, well, if in the limit of super large S, you recover some sort of Zipf law with an exponent that is characterized, that depends on the interurban migrations. So it's not a universal exponent. We saw that for the, it can be 1.2, 1.7, depending on the country. So it's not a universal thing anyway. And the other point is that, well, this is the first term of the expansion, but if you compare, for example, the first and the second term, when is it really dominant? When do you really see this Zipf law behavior? And you can do the math, and you find this expression that I wrote here. And basically, in practice, it shows that the population needs to be at least, well, at least 1 million, basically, to see this first term. So basically, in practice, you never see a nice power law with this exponent alpha. The finite size effects are too strong in some sense. And what is interesting is that you can ask yourself, well, but if it's this form, how come that I see some kind of Zipf law in the data? Well, you can actually try to make a power law fit of this complicated function. And this is what we did. For example, here we took alpha equal 1.3 here, and we took some reasonable values. And what we did is that we did some fit between a minimum value S min to the maximum of this complicated function. And we indeed found that the fit is very good. So it looks like a power law, but with some effective exponent that we show in blue here. And of course, when S min is very large, so when you are looking really only large values of the population, you recover this 1.3, which corresponds to the alpha here. But in general, it means that you can make a power law fit of this complicated function and see some effective exponent that will depend on many things, of course. But so you can have this artifact, this spurious exponent. So it looks like a power law, but the exponent is not simple. It's an effective exponent. And let me skip this. So, and this leads us to the validity of the Zipf flow. So if we believe this equation, it tells us that the distribution P of S is not a power law. It's a complicated thing. In general, could be a function of Fox function and things like that. So it's not a power law, and we don't observe Zipf flow in general. What we see is some spurious behavior is that you make a power law fit on some range, and actually in many empirical analysis, the range is changing. People are fitting only where it's more or less straight in the log-log plot, but you usually see some curvature that people ignore. But we understand here that no, in general, it's not a power law. And you have this very important finite size effect. So it depends on the, in fact, on the range of cities, of population that you have. And if you make a power law fit, you will get an exponent that is a mixture of the noise, of finite size effect, of the fitting method, etc. And this is how we explain the different values of the Zipf exponent that I show you here, this histogram of the alpha values, which can be very large or very small. And this is because, in fact, we don't have a power law, a nice power law in general. So, but we can, if we claim that's the correct equation, we can go a bit further, because we showed that, okay, we recover some complicated function that could explain the diversity of exponent measured. But if the equation is correct, we should also be able to say something about the dynamics. And in fact, most of the model were focusing on the Zipf flow. They were not saying anything about the dynamics. So the idea here is, okay, what is the equation saying about the dynamics? And the dynamics is not trivial. Here I show a very simple example of a few 5 cities in France, and it's a representation which is called the rank clock representation. So basically the radius is depends on the rank. So the rank 1 is on the largest radius here, and if you go to larger and larger ranks, you go to closer to the center. And the angle is proportional to time. So you have to read it as a watch. Here it's counterclockwise. And so you start from 1876. This is the blue curve. This is Paris, which stays basically rank 1 all the time. And then you have some other cities. And you see here that, for some reasons, they can really shrink or increase a bit. Here, the red one shrinks, and this is the case of Decazeville. And there was some mining industry here. And what you see is that in the 60s, typically, this mining industry was closing. And so population started to decrease. People were starting to go away. So you have a non-trivial dynamics. The rank is not given for all the time. And if you look for the system, here it's for France, the data was the best for all this. So the real data here, this is the rank clock for the most of the cities in France. And you see indeed some turbulence. So you see many changes of rank. And if you start with the same initial condition and apply the Gabet model, you get something that is super quiet. In fact, you don't see these rank changes. So the Gabay model, in fact, even if it reproduces some sort of zip flow, it's totally unable to explain the variation and the rank variation. And here we redid the same experiment with our equation, with this Levy noise, and we indeed see some fluctuations. Of course, you can go a bit further and measure things. And for example, here on the top left, you can look the probability, the cumulative distribution for the rank variation. And you see that indeed the empirical measure, this is in black for France, you see indeed some variation of order 200 or 300. So some cities are changing rank from 200, I mean, from 2 to 202 and so on. So you see this huge rank variation. And the Gabay model is completely unable to explain this large variation. It's basically here, it stops at 150. So in the Gabay model, you never see this huge rank variation. And this is in contrast with this kind of, with our equation, where indeed we can have super large rank variation. And you can confirm this with the distribution of the rank variance, this term here. And this is basically on the top right. And this is the 1 minus cumulative. And you see indeed it confirms this result that the Gabay model is unable to explain a super large rank variation. So on the bottom, this is the case for the US. The data is less good and results are less clear, but still on some quantities, you can see that the Gabay model is really unable to explain what is going on. You can go further and look at other quantities. So we tried many things, and here it's, for example, the time that it takes to see the maximal rank variation. So you look for a city, you look at its maximal rank and the minimal rank. This is the delta R here, and this, to observe this rank variation, you need a certain time, T max minus T min. And this is what we represented here. So it's the number of years that it takes to observe the maximal rank variation. And again, the Gabay model never sees variation up above 100 or so. So it's completely unable to explain the empirical result here in blue, where you see over almost 100 years rank variation that are of the order 200 or 300. While in the Levy model, the agreement is of course not perfect, but we do observe this super large rank variation in the dynamics coming from the equation. That's the important thing. The equation is able to generate a turbulent dynamics consistent with empirical data. So then let me, I'm concluding now. So then we see that we both are able to explain the diversity why the zip flow, in fact, is not correct for cities, but you obtain something which looks like a power law, but it's not really a power law. And by fitting with a power law, you obtain an exponent that cannot be universal and that cannot be super simple because it will depend on many details. So the thing is that here, the important term is this Levy noise, which reproduces the dynamics of the interurban migration, and it tells you that you have some migration shocks. So for some reason, in the history of cities, suddenly many people are going to a given city. Think about the gold rush in San Francisco. San Francisco had a population of 1,000, and the year after, in 1850, something like that, 1 year after, the population was 25,000 because people were digging for gold, and there was this rumor that there's some gold around San Francisco. This is an extreme case, but it shows that there are some shocks where people suddenly go to a city because there's some activity, or of course the negative case also exists where suddenly there is some a change of activity, a decline of an industry, and people are going away looking for a job elsewhere. So, and these are the shocks which really govern the evolution of a city, because if we only add the Gibra equation, all the rank, etc., would be constant. So the city, cities in the country would evolve, but the rank would always be the same, and nothing super exciting, And the fact that you have some rank changes, etc., is that it's because of these shocks that could be super important. So, and it also means that you can change the fate of a city. If it, it's not written in stone, its rank. A city can indeed become super important in the country or disappear in the negative case. So it underlines the importance of, let's say, of measures to make a city attractive. That's an optimist message. And let me just spend a few minutes about, so what next then? And I think that the next step is really to understand the spatial aspect of city growth. And we did the first studies recently, and we showed that interurban migration are indeed depend on space. And long story short, we showed that basically when you move from a city to another one, basically people are moving, coming from the core, let's say the core center of a city, they are moving usually in the core of another city. In contrast with intra-city movement, where this was done in the US only, but where, for example, basically people moving from downtown or from the core center of a city, usually if they stay in the same city, they are moving in the periphery, usually to get more space. So we have these different flows which depend on space, which can explain a few things on how a city grows at the finer scale. But I think that even more interesting is this type of figure, is that this is London from growing over a century. And so it was first in blue and then green. So this is the built-up area. And so this is, of course, what can we write some equation for the local for the local density, for example, or local population density? This is really, for a physicist, I think it's really, how can I say, annoying, because it really looks like, surface growth that we saw in many cases and many in experiments. So what could be the equation for this? And this is a totally open subject. So, of course, as a physicist, you could think of, there was some attempt to describe this as a diffusion limited aggregation model, the DLA. You can think of something like a bacterial colonies growth, where you observe different morphology for different coefficients. But an additional problem, I think, is that the cities that do not evolve in free space. You have an interaction with the road evolution typically and the transport network in general, which means that you have preferential direction of growth. And probably if you want to write an equation for the spatial evolution of a city, you have to take into account the coupling with between infrastructure and population density. And then, of course, also you can ask yourself, maybe the economic activity is important. So it's certainly a difficult problem, but I must say that so far we don't really have a clue about how to attack this problem. I thank you for your attention, and I stop here, and I'm happy to answer your question.
Thank you, Marc. Let's end our speaker.
Thank you.
So please put your questions. Yuri Volovac, please.
Thank you very much for the talk. I have two questions. The first one is, as far as I remember, 2008, it was the year when half of population of Earth started to live in cities. And now this share of citizens of cities is increasing. But now when you were speaking about your model, these people were traveling from city to city. Does it mean that this migration from villages to cities is irrelevant on the scale you are speaking? And also from cities, obviously, to the villages?
It's not, these are small numbers, so it seems that so we would need more data to check, but it seems that it's really, let's say, the most important terms are from medium-sized city to large city, things like that. The rural to urban are much smaller numbers, of course. It would be interesting to see, especially in Western countries, we saw some people going back to mid-size, medium cities after the COVID, in fact. And it would be interesting to see now what is happening. So, but more generally, I think that we need to understand the statistics of this interurban migration. It's not so clear. Here we have aggregated term that behaves as a Levy noise, but it doesn't tell you exactly what is happening in the country, you know. So it would be interesting to see at a finer scale what is really happening and how it's changing with time. And even we don't have a model, in fact, for interurban migration that gives a power law distribution. I mean, why do we see this capital X, which is 1 over x to some power 1 plus alpha? Why is it a broad law? What would be a model? Maybe something based on, you know, on economic activity, for example. You know, if suddenly a city becomes attractive, it will attract many people. Is it enough to create a power law distribution of migration? I don't know, in fact. But this is the crucial. This is, of course, of crucial importance. Here we see the thing, you know, on a really aggregated scale.
Thank you. And then, if possible, another question. I think some 15 years ago, at least, it was the series of Jeffrey West papers about evolution of cities. Certainly you are aware about. And there he discussed processes which are going on in these cities, and some of them were governed by sublinear scaling, some of them were governed by superlinear scaling. And the conclusion of this reasoning, as far as I remember, was that every city, when it is born, it encodes the date when it will be dying, when it will vanish. And he was showing some statistics for American cities. And then the comment was that why cities survive? Because at some point comes some very important innovation. And because of this innovation, so to say, the clock starts to count new time. And then the differences between these innovations with a span of time are shorter, and now we need kind of very important innovation every several months. Of course, you were not speaking about these things here, but what is your opinion about this kind of reasoning?
Well, I think, you know, this has to do with the dynamics of all the cities, right? Why it's turbulent, why the rank are changing, why suddenly a city becomes important, why another one disappears. In our equation, there's nothing. Actually, again, we describe the statistics. So we have nothing to say about the particular fate of a specific city. That's the weakness of this approach, in fact, is that we say something about the distribution, about the statistics of rank variation, but what is going on at the level of a particular city, the model, the equation says nothing, basically. This is encoded, in fact, in this Levy noise. So you have this huge variation, sudden variation of people coming in or going out. And of course, this is the important, how can I say, again, it has to do with why a city becomes attractive or not. So the decline and the rise of cities. And it has to do, of course, with innovation, new activity. We see, for example, there are some, in the US, you can think about Detroit. Detroit, you know, since the decrease of the automobile, the car industry, people went away, we had this subprime crisis, etc. But now the thing is that Detroit is rising again because of some innovation, startup being there, etc. And so I would agree that an important ingredient is new, maybe innovation in a broad sense. I mean, new activity or something that really governs the attractivity of a city. And again, a model that could explain this interurban flow would rely on the attractivity of a city, which depends, of course, on innovation, etc. So I think the full model, if we would like to describe in more detail these inter-urban migration, here we show that these inter-urban migration are fundamental to understand the population evolution. These are fundamental quantities. But we didn't provide any model for these quantities. Yeah. And that would be the next step, I believe. A very interesting thing to do.
Thank you.
Thank you. Please, another question. Please, right hand folk.
I heard the car, but no question.
Reinhard, unmute, please, your microphone.
It's still muted. It's still muted. We cannot hear you.
Now it is okay, I think. Oh, now muted again.
I can hear. I think it's muted.
If I can share my experience from yesterday, when you unmute microphone, some delay is between it starts working. So now it is indeed muted. So you should unmute and then wait, and then it's muted.
No. That's not working, it seems. If there is a... Okay, that's okay. So I guess that, yes, indeed, in this, in order to construct the equation, you have to define a system. So you have to define what is in and what is out. And it's true that the Zipf law was measured at the level of countries, but also many countries. For example, you can construct the Zipf law for, let's say, European cities and things like that. And this, once you define some borders, let's say some system with specific borders, it will then define what we call inter-urban migration. So if you look, for example, the Europe, then the whole Europe, inter-urban migration will be between, Berlin and Paris, etc. So then it changes the definition of inter-urban migration. So and this is important because it might change the statistics. So the flows and their definition, their statistics will depend on the border. That's very clear. So if you do the whole world, for example, then, migration from Buenos Aires to Paris is a flow like from, whatever. So it's very important to define indeed the borders, because again, it might change the statistics. And here we face the problem that we don't have so much data from urban to urban migration at different levels, but definitely the statistics, or the statistics changes for these different flows, that would be super interesting. But here it's vital to define a system so we know what we speak about. It characterizes then the flows. We know what we talk, the inter-urban flows, again, which depend on the border, and this leads to the equation that I was talking about. If you change the borders, you might have another equation. I mean, a similar equation, but with different statistics. Of course, I don't know if I answered really the question, but this is what I guessed about the question.
Okay, we have some time. Probably someone has a question.
Is there?
So if there are no questions, let's thank our speaker again.
Thank you very much. Thank you. So I will. Thank you. I will now mute myself. Thank you. Thank you, Raphael.
And I guess we have a coffee break to 4:30.
4:30 in view.
Yeah.
Excuse me, do you hear me now?
Yeah,
now,
yeah.
yeah, we do hear
Yeah,
you.
so could I ask my question again in some case?
If Marc is still here.
Is Marc still here?
Yes, I'm still here.
Yeah. So what I read on the participation. So I think of, when I think of borders, I mean, you only have countries which I think are democratic and so on. But the interesting thing would be, what was the effect in Germany when the border was opened? You have a lot of cities, maybe you have material for the German cities or the European cities, which were after that time connected, and you could see the change. Do you have such material?
I'm not sure. You mean I'm not sure about the German case. You mean after the reunification?
Well, there is first there was the breakdown in Berlin, and then the communication with East Germany, and then you also had in the time before the breakdown of the Iron Curtain and such things.
Well, I didn't look specifically at this point, but we certainly have the data. And
yeah,
I must say that Zipf did an interesting study, not about Germany, but it was at the time for the US at the time of the Civil War. And in fact, what he showed is that the zip flow is very noisy. You don't have a nice straight line. And interestingly, Zipf said, well, it's strange. We don't have a clear, nice power law. It's probably the sign of an intranational instability. So it was interesting because the fact that you have indeed some very noise curve is really the sign that something is happening. And in the US, it was between north and south. But I would expect some sort of of behavior when indeed during turbulent times, and especially for Germany. Yes, that would be interesting to check.
Yeah, because I also think you hadn't an external force, I think, in your stochastic equation. You could have an external force which acts on a certain city or on a certain type of cities. And then I mean, that's easy. If some economic strange thing is happening, the most important industry is going down or so, or if there might be also a difference in America, the data you showed between the cities at the ocean and the cities which are within the country.
Yeah.
This is the surface effect, I think you spoke about.
Yes, very probably. Yes. We have to, but it should be, again, the population. The nice thing is that population data is easy to get. What is super difficult is to find the data, the inter-urban migration. So the census about how many people move from city A to city B in a given time. That's unfortunately. Actually, for the German case, I remember that we tried to get the data, but it's not completely open, unfortunately. So we try to get it, but that's really the bottleneck in the study. because the population data it's easy to get, but the movement, the flows, that's really the difficult data to get.
Okay, thank you very much.
Thank you.
Thank you.